Hello, everyone. My name is Rishav Sarkar, and I'm so excited to present our work on a fast, accurate, and open source simulation tool for high-level synthesis. In this talk, I'll start with some background information on high-level synthesis, also known as HLS, and current methods of simulating HLS designs. I'll describe our key insights and introduce our new simulation tool, Lightning Sim, including a description of its architecture and some evaluations of its performance and accuracy. Finally, I'll conclude with some quick notes on open source, including where you can find our code, documentation, and tutorials for Lightning Sim. So let's get started. High-level synthesis is gaining popularity as a method of developing hardware designs. Users describe their designs in terms of a software language such as C or C++, and the HLS tool will synthesize that into hardware code in Verilog or VHDL. This is great for a few reasons. It's easy to learn, taking say 1 month. It's high productivity, letting you make complex designs in 1 month instead of 6, or even 1 day instead of a month. And it's easy to debug, since many issues can be found using standard software debugging tools. But you might have some questions about the performance and correctness of this generated code. That's where simulation comes in. Designers have 3 tools at their disposal. First is C simulation, which performs a high-level functionality check by simply compiling and running the software code. Next is the synthesis process itself, which, while not really simulating anything, does estimate the latency of your generated design based on static analysis. Finally, C RTL code simulation performs a full simulation of the generated RTL code for cycle-accurate latency estimates and an in-depth check of the functionality of the design. So, if you want to check the correctness of your HLS design, you have 2 options. You can perform C simulation, which is limited in scope and not necessarily a reliable indicator of the correctness of the generated design. Or you can do C RTL co-simulation, which is much more accurate. For HLS design performance, you also have 2 options. You can look at the HLS synthesis report, which has rough estimates for your latency that may not be necessarily reliable, or you can again perform C RTL co-simulation, which is much more accurate. So there seems to be a trade-off between the speed at which you can obtain simulation results and the accuracy of those simulation results. What if there was a way to get C-like simulation speed with CoSim-like accuracy? Introducing Lightning Sim, which isn't a trade-off but actually has advantages of both sides. In contrast to C simulation and C RTL co-simulation, Lightning Sim achieves fast simulation that provides latency estimates at the cycle level and deeper functionality verification than C simulation alone, while also introducing novel features never seen before, like incremental stall analysis for data flow designs when you change FIFO depths, as well as suggesting the fastest FIFO depths of your data flow designs. To understand how we do this, we need to take a closer look at the synthesis process itself. HLS synthesis starts with front-end compilation, which generates LLVM-IR, an intermediate representation consisting of low-level instructions. Within each function, these instructions are then statically scheduled into a finite state machine that controls their execution. This determines which functions can execute simultaneously and how loops are pipelined, for instance. The interesting thing about the resulting schedule is that each FSM state is usually equivalent to 1 clock cycle, which means that this FSM schedule could be useful for performing a cycle-accurate simulation. We also recognize that if we only need the FSM schedule to compute clock cycles, then we might not even need the generated RTL code at all to perform cycle-accurate simulation. With that in mind, let's define a few terms. We say the FSM schedule consists of static stages, which are the scheduling results that reflect only the potential simultaneous or sequential executions of modules and operations. For example, if 2 functions or operations execute together, they will be scheduled into the same static stage. Additionally, in something like a loop, the same static stages might be visited multiple times during execution. We define dynamic stages to be actual stages executed under a given workload. For instance, if a test bench executes a loop 4 times, the same static stages will be replicated 4 times within the dynamic schedule. To get from this dynamic schedule to our simulated cycle count, we need to consider stalls, which might occur for several reasons in our simulation, like function calls, FIFO reads and writes, or external memory operations. We denote all these potential stall points as events. During stall calculation, our simulator determines which of these events actually become stalls, and if so, for how many cycles they're stalled. That brings us to the key idea of Lightning Sim. We can obtain static stages from HLS synthesis from the scheduling process. We can figure out the dynamic stages based on the test bench execution trace, And based on that, we can identify events and resolve stalls to compute the final cycle count. WritingSim's architecture consists of a decoupled two-stage simulation flow. We compile and run LLVM-IR under a test bench to collect a trace that can then be analyzed to calculate the design performance. Let's first look at how this trace generation process works. The goal of trace generation is to take the HLS-generated LLVM-IR and get it to run under a test bench and determine what instructions are executed under that test bench. This isn't possible as is, because certain functions in the LLVM-IR are placeholders for HLS synthesis and are otherwise undefined and therefore can't be compiled. Thus, we generate our own implementations for these functions based on pre-written templates. Then, we need a way to figure out which instructions actually execute when we compile and run this code. LLVM-IR is organized into basic blocks, which are groups of instructions that always execute together. Therefore, logging which instructions are executed reduces to just logging which basic blocks are executed. We insert a call to a tracing function at the start of each basic block. Now this code is ready to compile and run. It produces a flattened trace of LLVM basic blocks that executed, the FIFO reads and writes, and external memory transactions. Using the LLVM-IR for reference, we map this flattened trace into a function call hierarchy. We can then analyze this trace to calculate the design performance. We first perform a process we call schedule resolution. In schedule resolution, we look at each function and compare its static schedule with the list of basic blocks that were executed in the trace. Using a list of rules based on how the HLS-generated FSM traverses the static schedule, we unroll it into a dynamic schedule for this function execution, essentially figuring out which FSM states would have been visited in what order if these operations were executed in the generated RTL. As we noted earlier, in this dynamic schedule, each stage is usually one clock cycle, except when stalls occur. For this reason, once we have the dynamic schedule, we identify all the events in it. Recall that events are all the potential stall points in the schedule, which include when a function call starts or ends, when a FIFO is read or written to, or when an external memory transaction occurs. Once we have this list of events, the next step is stall calculation. To understand how this works, let's consider, when and why do events cause stalls? Well, some events have to happen before others. For example, consider a data flow design, where a producer function is writing to a FIFO that a consumer function is reading from. If the consumer function is ready to read an element before the producer function has written that element, then the consumer function will be stalled until the producer function writes to the FIFO. Graphs are a natural way to encode these happens before dependencies between events in our simulation. We can have an edge in the graph encoding that a FIFO write must happen before a FIFO read. The challenge is that some of our dependencies are unknown during static analysis and must be captured on the fly. For example, dependencies based on a FIFO's depth. Our solution is to create a partial graph with statically known dependencies and dynamically resolve the unknown dependencies later. Here's an example showing how we construct a graph from lists of events. Each node in the graph represents a dynamic stage in one of the function executions, and each edge represents a happens before dependency, as we just mentioned. Initially, the only edges are between consecutive stages in each function, indicating that each dynamic stage happens at least one clock cycle before the next. The first event we encounter in our top function is the start of a call to the consumer function, so we draw an edge indicating that the consumer function starts after the corresponding stage of our top function. The producer function starts one stage later, and we draw an edge accordingly. In the dynamic schedule of the top function, the producer function ends at stage 4. So we draw an edge from the end of the producer function to this fourth stage of the top function. This encodes that if the top function reaches stage 4 before the producer function is finished, it will stall at stage 4 until the producer is done. We similarly draw an edge for the end of the consumer function call. We then consider the FIFO write and read events in the producer and consumer functions. The first FIFO read must happen after the first FIFO write. The second FIFO read must happen after the second FIFO write, and so on and so forth. At this point, we've successfully encoded all the FIFO read after write dependencies within our graph. But what about write after read dependencies? These occur because a FIFO cannot be written if it is full, that is, if not enough elements have been read from it yet. but this depends on the FIFO size, which is not known yet at this point in our simulation. Our solution is to draw what we call a floating edge to each FIFO write in the graph. This floating edge will be resolved later based on the FIFO depth. For example, if the FIFO depth is 1, the producer's first write will never have to wait because the FIFO will always have space for one element at the start. For this reason, when we're traversing the graph, we'll simply ignore this floating edge. When the producer performs its second write, if that first element hasn't been read yet, then the FIFO will be full, and the producer will have to wait until the consumer performs its first read. Therefore, we resolve this floating edge to the consumer's first read, which occurs at its stage 3. Similarly, the producer's third write cannot occur unless the second element has been read. So this floating edge for the producer's third write will resolve to the consumer's second read, which is at stage 4. And the fourth write's floating edge resolves to the third read at stage 5. However, if the FIFO depth is instead set to 3, then the floating edges for the first 3 writes will all be ignored because the FIFO will always have space for the first 3 elements. And the fourth write need only wait for the first read, after which the FIFO will have space for it. In general, the nth write to a FIFO must wait for the read at n minus the FIFO depth. Now that we've constructed the full graph, determining the final cycle count of our simulation is as easy as finding the longest path in the graph, which is a linear time operation. This also gives us the novel ability to perform really efficient design space exploration for FIFO depths. We can compile the graph once and quickly perform graph traversal many times with different FIFO depths. Furthermore, this design space exploration can easily be parallelized across all the cores of a system. The graph can reside in shared memory, and each core can traverse the graph without needing to copy or modify it. This is a very fast process, especially in contrast to co-simulation, which must rerun the entire simulation if you change any of the FIFO depths. We've evaluated Lightning Sim across 33 benchmarks, including 23 designs from Vitis HLS sample repositories, 5 implementations of popular algorithms from the Parallel Programming for FPGAs book, and 5 complex graph neural network accelerator implementations from FlowGNN, which clock in at over 1,500 lines of code each. We compare our simulation accuracy and performance against the synthesis and co-simulation estimates from Vitis HLS 2021.1. Our evaluations have also earned badges for reproducibility at FCCM 2023 and FCCM 2024. First, looking at Lightning Sim's accuracy, our results are an average of 99.9% accurate to the latency results produced by Vitis HLS co-simulation, with 26 out of 33 benchmarks achieving perfect cycle accuracy. Of the 7 cases that are not cycle accurate, 2 of them are only 1 cycle off, and the remaining 5 cases are within 0.2% of the co-simulation cycle count. You may wonder why Lightning Sim is not 100% cycle accurate in all cases. The reason is that we know that the model that we implemented for the AXI interfaces used for off-chip memory accesses is not a perfect model of the HLS-generated interfaces. In terms of performance, though, we achieve speedups ranging from 5 times to 146 times faster than co-simulation, with larger designs achieving the greatest speedups. On one of the graph neural network accelerator benchmarks we tested, co-simulation took 1 hour 10 minutes to complete, while Lightning Sim took only 29 seconds. Additionally, we see even better results for incremental resimulation with changed FIFO depths, which took less than 20 milliseconds for all the benchmarks we tested. This gives designers a powerful new tool to evaluate deadlocks and stalls in streaming data flow designs. Finally, we'd like to mention that Lightning Sim is available now on GitHub and licensed under the open source AGPL license. We've packaged it as a Conda package to make it easy to install and use, and we also have a tutorial available on our documentation website. Thanks for your attention, and we apologize for taking away your best excuse to slack off.